Welcome to the Deep Dive. Look, if you feel like the world of AI is just accelerating at this unbelievable pace, well, you're absolutely right.
It really is.
Breakthroughs are happening so fast, it feels like a full-time job just keeping up.
Uh-huh. Tell me about it.
But that's exactly why we're here. Today, we're taking a deep dive into some of the most significant AI research papers that dropped just last week, June 9th to 15th. We've pulled these from a top AI newsletter.
Good stuff.
Yeah. And our mission basically is to quickly pull out the most important nuggets from these, cutting-edge papers. Give you a shortcut to being really well-informed about what's coming next in AI.
Mm-hmm.
And honestly, there's some truly surprising things in here, stuff that highlights why this all really matters to you.
Precisely. And what we're about to explore, it isn't just theory, right? These are actual tangible steps. We're talking more capable, more efficient, more versatile AI systems. And a lot of this is already being put to practical use, or it's, right on the verge of fundamentally changing how AI learns, how it reasons, how it interacts with the world.
Okay, let's unpack this then. Maybe starting with how AI is getting smarter about how it learns, how it
Yeah.
adapts.
Good starting point.
Because traditionally, if you wanted to fine-tune an LLM, a large language model, for some new task, it could be, well, pretty cumbersome, very task-specific.
Oh, yeah. Very much so.
You'd need tons of data, loads of compute power for every single new thing you wanted it to do. It was like retraining a student from scratch for every subject.
Exactly. And that's where this first paper, Text to Luray, or T2L, comes in. It's a really novel approach using something called a hypernetwork.
Hypernetwork.
And the real innovation here, the key thing, is that it generates these Luray adapters, that's low-rank adaptation. It generates them instantly, just from a natural language description of the task.
Instantly. Yeah.
Yeah, so it completely removes the need for that traditional, really time-consuming fine-tuning for every new task.
That sounds incredibly powerful, like for iterating quickly. But how does T2L actually do that? Generate these Laurier things so fast? What's the mechanism?
Well, think of the hypernetwork as like a tiny AI whose whole job is to instantly design the specific tweaks needed to adapt the bigger AI, all in one go.
Huh?
So T2L is trained specifically to generate these Laurier matrices for the LLM. The hypernetwork just outputs the weights needed, bang, single forward pass, super fast.
Okay.
And it has two main ways it learns. One is reconstructing Lauriers that already exist, and the other is supervised fine-tuning, but across lots of different tasks at once.
So it's not just faster, it sounds more versatile too.
Yeah.
What are the implications then? This instant adaptation.
Well, it's a potential game changer. It means AI could adapt to, a constant stream of new demands almost instantly.
Right?
It kind of democratizes advanced customization. Developers could deploy specialized AIs in minutes, maybe, not days or weeks.
Wow.
And the benchmarks look good, too.
Yeah.
T2L performs competitively in what's called zero-shot adaptation.
Zero-shot adaptation.
Yeah.
Can you just quickly unpack that?
Sure. It just means the AI can handle completely new tasks it's never explicitly been trained for. It just gets a description of the task and boom, it adapts.
It's like true generalization then.
Exactly. It's a real test of its intelligence. And T2L, it even outperforms standard multitask LoRa baselines. And on some specific tasks, like PIQA and Winogrand, it actually beats task-specific LoRa's.
No kidding. Even better than one trained just for that task.
On some, yeah. It really shows its ability to generalize to things it hasn't seen. And apparently you can steer it just by changing how you describe the task in plain English.
That's really neat. And they found it scales well too, like with more training tasks.
Yep. Scales well with the number of tasks, and it's robust to different ways you might embed those task descriptions, which is a good sign. Suggests it could be pretty practical.
Okay, so T2L lets models adapt instantly.
Yeah.
But what if models could, adapt themselves, learn how to learn almost?
Now you're teeing up the next one perfectly.
That brings us to self-adapting language models, or SEAL. This framework actually lets LLMs generate their own fine-tuning data, and these things they call self-edits, update directives, basically.
Yeah, it's like the AI is doing its own homework and correcting itself.
Uh-huh. Great analogy.
And the core mechanism is, well, it's quite clever. Instead of just feeding it raw data to update weights, the model generates natural language instructions, these self-edits.
Okay.
So these edits might be like restated facts or maybe parameters for optimization or even instructions to use a specific tool.
And then those edits are used for the fine-tuning.
Exactly. And the
Okay.
process of generating those edits, that's optimized using reinforcement learning, RL. The reward signal is basically how well the model performs on downstream tasks after applying the edits.
That makes sense. And the results, are they any good?
Pretty compelling, actually. So for knowledge incorporation, right? On a squad task where the model had zero external context.
Okay, tough task.
Yeah. RL training using SEAL's own synthetic data boosted accuracy from about 33.5% up to 47%.
That's a big jump.
It is. And what's really remarkable is that this actually beat the performance achieved using data generated by a much larger model, GPT 4.1, even though SEAL was running on a smaller model, Qwen 2.57b.
No, wait. The smaller model using its own generated data did better than data from GPT 4.1.
That's what the paper reports. It's not just better numbers. It suggests, maybe a future where AI isn't just learning from us, but actively improving its own learning processes. It hints at, well, more autonomous intelligence.
Yeah, that's a big thought. And what about other areas, like generalization?
Good question. For few-shot generalization, on a benchmark called RCAGI, SEAL learned how to configure things like data augmentation and optimization settings.
Okay.
It achieved a 72.5% adaptation success rate, which is a massive leap from just 20% without the RL component optimizing those self-edits.
Wow, okay. So it learned how to adapt better. But you mentioned limitations.
Right. Always important. SEAL is susceptible to catastrophic forgetting. It's a common AI problem. Learn something new, forget something old.
Okay. The classic problem.
Yep. And it's also computationally expensive, right? All that repeated fine-tuning costs a lot. So future work probably needs to look at combining SEAL with, say, continual learning methods to get around these issues.
Makes sense. A fascinating challenge. Okay, so that's adapting and learning. Now, how are these models getting better at, understanding the world and reasoning? This feels like the next big hurdle.
Absolutely. And that brings us neatly to Meta AI's VGPay-2. This is a scalable architecture for self-supervised video learning.
VGPay-2. Yeah.
And the goal here is incredibly ambitious. They're aiming for a generalist world model.
A world model, like an AI that understands physics, cause, and effect, that kind of thing.
Pretty much. An AI that can genuinely understand, predict, maybe even plan within the physical world. A bit like we do.
That's huge. How are they training something like that?
It's quite an interesting two-stage process. First, massive pre-training on action-free videos, over 1 million hours of internet videos and images just observing.
Action-free, so just watching stuff happen.
Mostly, yeah. Learning the patterns of the visual world. Then there's a much shorter post-training phase. Just 62 hours of unlabeled robot trajectories from a dataset called Droid.
Only 62 hours of robot data after all that video.
Relatively small amount, yeah. But the idea is that massive pre-training builds a strong visual foundation, and then the robot data helps ground it in physical interaction.
Okay, so what can it actually do? What does this VGGP2 enable?
It yields this really rich, latent video representation that's useful across a ton of tasks. Performance is impressive, state-of-the-art on motion-heavy tasks like something V2, Epic Kitchen's action anticipation.
Right.
It also excels in multimodal QA question answering involving video. And here's the kicker. This is without any language supervision during the main video pre-training.
Wait, no text labels during pre-training. It learned just from pixels.
Largely, yes. It suggests it's building a visual understanding of the world, how things move and interact, without needing text descriptions.
That's fascinating. So what does that mean for, say, robotics? You mentioned robot data.
Exactly. This is where it gets really cool. With just those 62 hours of robot video, it supports zero-shot deployment for grasping and pick-and-place tasks.
Zero shot again. So no specific training for the new environment.
Right, on real robot arms in unseen environments. No rewards, no demos, no lab-specific fine-tuning. It just leverages that learned world understanding.
That feels like a significant step towards robots that can actually operate in the messy real world.
It does, and they really scaled this thing up too. Huge dataset, 22 million videos, a big model VITG, 1 billion parameters, longer training, and it actually outperforms standard image encoders on video QA tasks, which shows it's really grasping the temporal, the time-based aspect, not just static images.
Very cool. Okay, shifting from visual world models to pure reasoning. What about reinforcement pre-training, or RPT?
Ah, yes, RPT. This is a really interesting new paradigm. It tries to properly bridge LLM pre-training and reinforcement learning.
How so? Aren't they usually separate stages? Pre-train, then fine-tune with RL.
Traditionally, yes. But RPT reinterprets the core pre-training task, next token prediction. It reinterprets that as a reasoning task.
Okay. How does that work?
Instead of just predicting the next word, it frames it as reason your way to the correct next word. And then it assigns a reward based on verifiable correctness. It applies RL during pre-training on huge amounts of just plain text.
So it's teaching the AI to think its way to the next word right from the start, not just mimic patterns.
That's the core idea. Teach it to reason from the ground up.
Intriguing. How does it actually do that teaching at each token? What's the method?
It's clever. At each step, before predicting the token, the model first generates a reasoning trace, like showing its work, a little chain of thought.
Ah, okay.
Then it predicts the next token, and if that prediction is logically correct, like a valid beginning of the actual ground truth sequence,
It gets a reward.
exactly, it gets a reward. So it's learning to produce correct reasoning and correct predictions.
And what's the payoff?
Hmm.
How does this compare to just standard pre-training?
Well, the claim is it fundamentally shifts how we think about AI reasoning. It suggests you can bake in this deep, verifiable reasoning right from the start, not just bolt it on later.
Does it actually work better?
Significantly better, according to the paper. It outperforms standard next token prediction and also traditional chain of thought methods that don't use RL during pre-training. It gets higher accuracy on tokens of different difficulty levels.
Hmm.
And here's a concrete example. RPT-14B, so a 14 billion parameter model, apparently matches or even exceeds the accuracy of R1 Quinn32B, a much larger model on the OmniMath benchmark.
Wow, okay. Smaller model matching a bigger one on math reasoning. That's impressive.
It is. And they also found strong scaling laws. RQT improves downstream RL performance and generalization. It learns faster and better on tasks where you can verify the answers.
Like math or coding, I guess.
Exactly. Plus, when they analyzed the reasoning traces it produced, RPT-14B used more sophisticated patterns like hypothesis generation, deduction, reflection compared to standard models. It suggests it's actually fostering deeper reasoning habits.
Fascinating. Okay, sticking with reasoning, let's talk about Magistral from Ancestral, their first reasoning-focused LLM line. What's the hook here?
The really unique thing about Magistral is its approach. Pure reinforcement learning from scratch. No distillation from bigger teacher models, which is a common technique.
Ah, okay. Usually you train a big model, then use it to teach a smaller, faster one. They skip that.
They skipped that. The core insight, and it's kind of surprising, is that pure RL can actually rival distillation for reasoning tasks.
Really?
Yeah. Magistral Medium, trained without any explicit reasoning traces provided during training, still got a 50% boost on AIM-24 pass at 1. That's a tough reasoning benchmark.
50% boost just from pure RL.
Seems so. And it performs on par with, or sometimes better than, other strong reasoning models like DeepSeek R1, again, without relying on distillation. It points to maybe a more direct, possibly more efficient way to build these reasoning models.
And didn't they find some unexpected generalization too?
They did. Apparently, multilingual and even some multimodal generalization just sort of emerged, even though it was only trained on textual math and code data.
That's wild, getting cross-modal abilities from text data alone.
It is pretty surprising. They also mentioned building an efficient asynchronous RL setup and using really detailed reward shaping, rewarding good formatting, correctness, penalizing excessive length, ensuring language consistency. All that careful engineering helps.
Makes sense. Okay, let's shift from pure reasoning models to a very practical application. Fixing bugs in code. Code researcher.
Yes, a deep research agent designed to tackle complex bugs in big software systems. Anyone who codes knows how painful debugging can be.
Yeah. Hours, days sometimes.
Exactly. So Code Researcher's method is quite sophisticated. It doesn't just look for simple syntax errors. It does multi-step reasoning over the code's meaning, semantics, common bug patterns, and even the project's commit history.
So it digs deep into the context, like a human expert would.
That's the idea, like an expert detective figuring out the root cause. It tries to understand the why behind the bug, not just the what.
And how effective is it?
Significantly better than previous agents like SWE Agent. According to their benchmarks on K-benches, it achieved a 58% crash resolution rate.
58%.
Mm-hmm.
That's actually huge for automated bug fixing.
It really is. It means the agent is effectively gathering and filtering the right information from across the whole code base before it tries to generate and test a patch. This could save developers an enormous amount of time.
Definitely a tool many would want. Okay, now, reasoning often involves pulling information from different places, right? Text, tables.
Ah, yes. And that's a common weakness in current RAG systems, retrieval augmented generation. They often struggle with documents that mix unstructured text and structured tables.
Right, like reports or web pages?
Exactly. Typical RAG tends to just flatten the tables, mix the cells with the text around them, and you lose all that crucial structure.
Which makes complex reasoning really hard.
Precisely. You can't easily do calculations or lookups across rows and columns if it's all just jumbled text. This really limits multi-hop reasoning over mixed data.
So what's the solution?
That brings us to TableRag. It's designed specifically for this. It's a hybrid system. It integrates SQL-based symbolic execution, basically, running database queries with standard text retrieval.
SQL and text retrieval together.
Yes, in a unified iterative framework. It's designed to truly understand and reason over those mixed data types while preserving the structure.
How does it work iteratively?
It operates in 4 main stages, repeating as needed. First, it decomposes the query based on context. Then it retrieves relevant text passages. Then, crucially, it generates and executes SQL queries on the tables.
So it actually queries the tables like a database.
Exactly. And finally, it generates intermediate answers, combining info from text and the SQL results. This iterative process keeps the table structure intact.
And the results. Does it work better?
Consistently outperforms prior methods, things like NaiveRag, React, TableGPT-2. They report over 10% gains in accuracy on a new benchmark called HitQA.
HitQA.
Yeah, it covers like 300 multi-hop questions across different domains and different types of table operations.
Yeah.
So pretty comprehensive.
Why does it work so much better, though?
They did ablation studies taking parts away to see what breaks, and it showed that the SQL execution part is absolutely critical for any kind of nested reasoning, like calculations within the table.
Makes sense.
But the textual retrieval is still crucial for finding the right entities or numbers mentioned in the text to use in those SQL queries. It also seems more efficient and robust, solving most problems in 5 steps or less.
Very clever combination. Okay, finally, let's look at some new tools and infrastructure making AI more accessible or powerful. First, ComfyUI R1.
Right. So ComfyUI is a popular tool, especially in the AI art scene, for building complex image and video generation workflows using nodes.
Yeah, it's powerful but can be intimidating.
Exactly. So ComfyUI R1 is a 7 billion parameter model fine-tuned specifically to automatically generate those ComfyUI workflows based on a user's request.
Automating the workflow creation, that's cool. How's it trained?
A 2-stage pipeline. First, supervised learning using chain of thought examples, teaching it how to reason about building workflows. Then reinforcement learning to fine-tune it further based on how well the generated workflows actually work.
And performance, how does it stack up?
It significantly outperforms previous methods, even those using big commercial models like GPT-4o or Claude 3.5.
Really? Better than GPT-4o?
On this specific task, yes, it achieves like 97% format validity, meaning the workflows it creates are actually usable in ComfyUI, and it gets the best scores on node level and graph level correctness.
Wow.
On their benchmark, ComfyBench, it boosted the success rate of actually executing the generated workflows to 67%. That's an 11% jump over the previous best.
So what does that mean for users? Less fiddling with nodes?
Pretty much. Qualitatively, it creates workflows that are more faithful to the user's request, more complex when needed, and more likely to actually run correctly. And the images generated tend to match the instructions better in terms of style and structure.
That can make tools like ComfyUI much more accessible.
Definitely. It lowers the barrier to entry for complex creative AI work.
Okay, next up, Lamar-L. Sounds like infrastructure.
It is. It's a fully distributed asynchronous reinforcement learning framework. Big words, but basically.
Basically.
Its purpose is efficient, large-scale LLM training using RL. Think training models from 8 billion parameters up to 405 billion, maybe even bigger.
Okay, so scaling up RL training, what's the impact?
Speed. They achieved up to a 10.7x speedup compared to DeepSpeed Chat, which is a common framework.
10 times faster.
How? Through a combination of clever techniques. Co-located model offloading, asynchronous training, fast GPU weight syncing, technical stuff. But the bottom line is it makes training these massive models with reinforcement learning much, much faster, while apparently maintaining the model quality.
So accelerating the development of the next generation of huge LLMs.
That's the goal, making it more efficient.
Got it. And for our last piece today, something with very tangible, real-world impact, AI predicting cyclone tracks from Google DeepMind.
Yeah, their weather lab has debuted this new interactive platform for AI-powered cyclone forecasting.
How does it work?
It generates 50 different possible scenarios, an ensemble predicting track and intensity up to 15 days out.
15 days. That's quite far ahead.
It is, and crucially, it's reportedly outperforming traditional weather models in these predictions.
Better than the standard systems.
That's the claim. And here's the really important part. It's not just a research project anymore. It's actually being used now by agencies like the U.S. National Hurricane Center to help with early warnings.
Wow, so this AI is already potentially saving lives.
That's the implication. Providing better, earlier forecasts directly impacts safety and preparedness for millions of people in the path of these storms. It's a fantastic example of AI having a direct positive impact.
Absolutely. A really powerful note to end the core discussion on. So we've covered a lot this week.
Yeah.
From making LLMs incredibly adaptable, almost teaching themselves,
Right, like SEAL and T2L.
to building these sophisticated world models like VJP2 that understand video and potentially the physical world.
And new ways of teaching reasoning from scratch, like RPT and Magistral.
And then all the way to practical tools, fixing code, understanding tables, automating creative work, and even predicting hurricanes. It's quite the range.
It really is. And it hammers home the point that this rapid innovation we're seeing, it's not just confined to academic papers. It's actively shaping the AI you'll be using, maybe even tomorrow.
Yeah.
And it's already making a difference in really critical areas like disaster prediction. It really points to a future where AI is not just, intelligent in processing information, but increasingly autonomous in how it learns and solves problems.
Well, that brings us to the end of another deep dive. We really hope you feel significantly more clued into the absolute latest in AI research after this.
And maybe something to chew on as you go. Reflecting on all these advances, Textalar's instant adaptation, VJP2 trying to model the world, RPT teaching reasoning differently. Which of these breakthroughs do you think will hit home first? Which might have the most profound or maybe the most immediate impact on your daily life?
Yeah.
Or perhaps what new questions do these leaps in autonomous learning and reasoning raise? What new ethical points or practical challenges do we need to start thinking about right now?